So thank you for joining my talk called the New Analytics Toolbox. The plan for today, and if you're not here for the New Analytics Toolbox, then you should probably find the other room. The plan for today is to talk about the state of big data analysis and how that's changed over the last couple of years. Hadoop, as probably most of you know, has dominated that space for many years now, but there are quite a few new tools available that are worth a look, whether you're new to the game or whether you've been using Hadoop for a long time. So who am I? My name is Robbie Strickland. I'm not British. I'm still getting used to the feeling that I'm saying everything wrong, so you'll have to forgive me. I work on the platform team at the Weather Channel, which is maybe not as well known here as it is in the US, but the reality is most of you use our data every day. If you use things like Google Now and iOS and Yahoo, and most of the data originates with us. So that's what I do. That's the team that I manage. We power weather.com, the TWC mobile apps, and most of, like I said, the weather data that exists in the world today. So the first question you might ask is, what's wrong with Hadoop? So by a show of hands, let me see who is working with Hadoop today. So just a small number of people. Maybe that's good. So who's running Cassandra in production? Okay, and who is using or planning to use Spark? Okay, interesting. All right, well, so hopefully this won't be too elementary. We'll see. So what's wrong with Hadoop? It works fine, right? You've invested all this time and money into it, so what's the big deal? Well, for starters, it's 11 years old, which is very hard to believe. Some of you, the Hadoop people in the room, might be thinking, well, I guess not the Hadoop people, the people who didn't raise their hands for either might be thinking that you're late to the game. But I would say to that this is actually good news for you, because you're unencumbered by your existing technology investment, unlike those Hadoop people in the room. So, and while it was groundbreaking at its introduction, it's actually pretty slow and inefficient by modern standards. And this is primarily because everything gets written to disk, including all the interim steps. And in many cases, you actually need a chain of jobs to perform your analysis. So you can't just, one single MapReduce job isn't going to do the job. You need multiple chained. If you've actually written any MapReduce code, then you know it's not the most intuitive API. We sort of put up with it because it's been what has been there to deal with. It's easy to get things wrong, and it's pretty hard to test. And actually, the cost of getting it wrong can be very high, which is kind of a bad combination. You've also seen that it requires quite a bit of code to perform even the simplest of tasks. And this is largely a result of the significant amount of boilerplate code and maybe the fact that it's in Java. This is also improved. This is somewhat improved by tools like cascading, Pig, Hive, and those sorts of things. But to me, that's really just more evidence that the core API is inherently burdensome. And if that weren't enough, it can be difficult just to get the thing working. I don't know if you've tried to do this, to roll your own, but it doesn't really do anything out of the box. It's like a box of tools that you don't know how to use. You have to do a lot. You have to read a lot of documentation, create config files that don't even exist, and that aren't intuitive, frankly, and fire up a bunch of separate processes to get it running just on your local machine. That's not even to get it running in a cluster. Fortunately, we are seeing a new crop of tools designed to solve many of these problems. This is a partial list of some of the more popular choices you may have seen, but the Hadoop ecosystem is already suffering from an overabundance of bolt-on components, which is part of the problem. So it's easy for the really revolutionary stuff to kind of get lost in the shuffle. So let's quickly break some of these options down to see what they offer. First, we have Cloudera's Impala and Apache Drill, which are both massively parallel query processing tools. They're designed to run against your existing Hadoop data. Basically, they give you fast SQL-style queries for HDFS and HBase, with the theoretical possibility of integrating with other input formats, although I'm actually not aware of anyone having done this successfully with Cassandra. Maybe someone has, but I'm not aware of it. And then we have other proprietary vendors that offer a variety of analysis tools, such as Splunk, Keen.io, those sorts of things. They're usually cloud-based and usually require you to send them your data, at which point you can run queries using whatever their API or UI is. Spark, on the other hand, and its SQL query API, provide a general purpose in-memory distributed analysis framework. You deploy it as a cluster and you submit jobs to it, very much like you would Hadoop. And then Shark is essentially Hive on Spark. So if you've used Hive, then you're familiar with the construct. It uses your existing Hive metastore, but it executes the queries on your Spark cluster. However, at Spark Summit a few months ago, it was announced that Shark will be ultimately replaced by Spark SQL, so it's effectively deprecated. So which tool or tools should you ultimately choose? Well, actually, the good thing is you don't have to choose one, because most of the major Hadoop vendors have embraced Spark, as has DataStax. So if you choose Cloudera or Hortonworks or any of these guys, then you get Spark sort of by default. But none of us are using those, of course, because we're all using DataStax, right? So this actually makes it an ideal Hadoop replacement. And if you haven't started using Hadoop, at this point, it may make sense for you to simply redirect your efforts towards Spark instead. There's been a lot of investment in Hadoop connectors as well, and if you know, they're called input formats, and these can all be leveraged in Spark. So you can still use your Mongo Hadoop connector, which I'm sure we're all employing, inside Spark, even though it was designed for Hadoop. And even though it makes use of the Hadoop components, however, you don't even actually need Hadoop installed. So you will need a distributed file system, and HDFS is a fine choice, but Hadoop is not actually a hard requirement. And also, unlike Hadoop, Spark supports both batch and streaming analysis, which is one of the places where Hadoop was really difficult to work with because you had to add something else, like Storm. And this means you can use a single framework for your batch processing as well as your near real-time use cases. And then Spark also introduces a fantastic functional programming model, and I'm a functional zealot, so I call it fantastic. You may call it, something you have to learn. But I think it's fantastic. And it's arguably better suited for data analysis than Hadoop's MapReduce API, and certainly better suited than Java. Ahem. So I'll show you the difference in a minute. And since I assume you're all interested in how well this works with Cassandra, the good news is you don't even have to use the Hadoop input format like we early adopters had to use, because DataStax has built an excellent direct Spark driver, and open source, I will add. So I assume since some of you raised your hands saying you're using Hadoop now, or you're planning to use it soon, let's quickly compare it with Spark. For those who are unfamiliar with what it looks like to write MapReduce, and let's not jump ahead. For those unfamiliar with what it looks like to write MapReduce, and maybe to cause a little post-traumatic stress episode for those who do have experience, let's look at a simple MapReduce job. So the use case for this job is our social weather feature in the Weather Channel app. And basically, what this allows you to do as a user, you can report that you disagree with what we report as weather conditions, or simply agree that, and just because you want to click on it. And it reports your current weather conditions the way you see them. This data is stored in Cassandra, and the basic idea is we want to create a simple histogram of check-ins by hour, which is nothing more than just bucketing them by a rounded timestamp. The first thing you'll notice is all the imports. That's a lot of imports for a rudimentary job, right? We're not really doing a whole lot here. There's no third-party APIs we're bringing in. It's just the basic imports. There's a lot of stuff going on there. And then we, kind of start with our configuration here. So we start configuring the job, starting by parsing some command line arguments. And then we finish off the config with another 50 lines or so, short 50 lines of boilerplate code there that we see in every single MapReduce job. After that, we'll have to create a mapper, which groups all the input keys by hour, and I won't bother to let you linger too much on this, but you can, if you're familiar with it, you'll understand. If you're not, you'll get the gist of it. And then, of course, you have to have a combiner, or who knows, if you've not written a combiner in something like this, you know that the job will take forever. You write a combiner and it cuts the time down exponentially. So we have to do that. This essentially pre-aggregates the counts before we ship it off to the shuffle. And finally, we aggregate all the hours and add up the counts in the reducer and then output them to Cassandra. 130 lines of code later, we have grouped check-ins by hour. And in case you weren't counting, only 5 lines, some of which had to be repeated for the combiner, of the 130 were actually devoted to creating the histogram. The rest of it was just Hadoop cruft. And now Spark. Let's have a moment of silence as we mourn the death of MapReduce. Okay, mourning over. As you can see, we've reduced our code by 107 lines. We have 2 imports, 2 lines to configure the job, then we're right into our logic. There are no byte buffers to parse, and the logic is easy to understand. So, now that everyone wants to use it, what is it exactly? So Spark is actually an in-memory cluster computing framework, as I said. It's built in Scala, which means it runs on the JVM. It can be 10 to 100 times faster than Hadoop MapReduce, which you've probably seen quoted, and I can only tell you that we have found it to be true in a lot of cases. And this is primarily because it runs in memory and avoids all of the disk I/O. Not all of it, most of it, I should say. As you saw in the brief glimpse of our sample job, its API looks a lot like the Scala collections API, assuming you're using Scala, because we all are, except that you're working with large distributed data sets instead of just your in-memory data set. It has a native language binding for Scala, Python, and Java, and there's a separate project called Spark R, which is designed to enable R on Spark. And this is actually a fantastic way to let your data scientists play with Spark if you're using R. R is really, really good for data exploration. It offers stream processing capabilities using the same collections API, so you only have to learn the one paradigm as opposed to having to learn to write MapReduce code or pig code or Hive code and then turn around and learn how to write storm topologies and all those sorts of things. You've got one API to rule them all. And as I mentioned earlier, it also supports any existing Hadoop connectors, so you can use Mongo. Spark also offers some interesting additional features, including a native graph processing library called GraphX, and as well as a machine learning library called MLlib, which is, if any of you have used Mahout, it's really what Mahout always wanted to be on Hadoop, but never was. And Spark SQL gives you the ability to run SQL queries over any Spark collection, so there's no additional bolt-on tool or query framework that's required. And if you're a fan of Elastic MapReduce, you'll be happy to know that you can enable Spark out of the box on an EMR cluster as well. So I will say they're usually a version or so behind, but if you're not into bleeding edge, then it works fine. One of my favorite features of Spark is the ability to join data sets across multiple disparate data sources, which we do have at the Weather Channel. Imagine doing your joins across Cassandra, Mongo, Riak, whatever data stores you have, and HDFS data in a single job. It is actually quite powerful for that purpose. So now let's take a step into how this, take a look at how Spark integrates with Cassandra. So DataStax, as I said, has recently open sourced a fantastic Spark driver that's available on their GitHub repo. And it gets rid of all the job config cruft that early adopters of Spark on Cassandra had to deal with. And there's actually no longer a need to go through the Spark Hadoop API, which was pretty annoying. You still had most of the job configuration stuff that you have in a normal Hadoop job that you had to deal with. And the good thing is, too, it supports server-side filters, which I don't know if any of you guys saw the talk a couple of talks ago on some of the work that, I forgot their name already, but that they're doing with the server-side filtering, building in Lucene. But that's some pretty fantastic stuff that I'm actually interested in taking a look at as well. You should take a look at that if you haven't. But this can save a huge amount of processing time and overhead, since Spark never has to look at the data that you don't care about. And as with the Hadoop integration, it knows where your data lives on the cluster, so it's locality aware. And it will try to load data locally if possible to avoid network overhead. And Spark still does, as I said, require a distributed file system of some kind for checkpointing, but this is sort of a low overhead usage. Personally, I find it useful to go ahead and have HDFS running so that I can throw unstructured data into my analysis cluster alongside the Cassandra data. So what does this all look like on a physical cluster? A lot of people get this wrong, which is why I throw this in. So let's look at what an analysis data center looks like running Cassandra with Hadoop, because a lot of people are doing this already. You can see that in the canonical setup that you have your Hadoop master with the name node, the secondary name node, and the job tracker. Then you have your Cassandra ring with co-located data nodes and task trackers. This is the canonical setup, so that this allows the local Hadoop task trackers to understand where your data is and pull it from the local node. Spark actually looks very, very similar to this. If you assume you're running HDFS, then you'll still have your Hadoop name node and secondary name node, and then data nodes running on each Cassandra node. That's again, for HDFS. But you'll replace your job tracker with a Spark master and your task trackers with Spark workers. So let's talk about what it actually looks like to build a Spark application. Here's a high-level view of that. The main entry point is the Spark context. The context takes an instance of a Spark configuration, which defines the job and the task properties. The Spark application will then load data from a data source and serialize it into a Spark RDD, or Resilient Distributed Data Set. We'll talk about what that is in a minute. And next, we'll perform a series of operations on the data, and these operations come in the form of transformations and actions. And finally, we'll save or display the resulting data or calculation. So, what is an RDD? Well, it's a distributed collection of items that's partitioned across the cluster. You can sort of imagine it like the way if you write a file into Hadoop, it gets split into blocks and written across the cluster. It's a similar sort of concept in a resilient distributed data set. It has an API that's very similar to that of the Scala collections API, as I showed you earlier. It allows the transformations and actions operations on the data. And all the operations are actually performed lazily across the cluster, so they're not actually executed until you have to materialize the data set. RDDs are also the key component to Spark fault tolerance, because they can recalculate values from any step in the job in case of a worker slowdown or node failure, and Spark does a very good job keeping track of that. Spark will automatically detect the failure and redistribute the work to other nodes in the cluster. So let's look at transformations versus actions. Transformations produce new RDDs, and that's actually, if you're looking at the API, how you can tell the difference. If the return value is an RDD, you know it's a transformation. By contrast, actions actually require full materialization of the records to produce the value. And this is obviously more costly than the lazy transformations. And you can tell the difference with these because they produce usually, depending on which language binding you're using, they produce a language-specific collection. So some examples of transformation include things like filter, map, flat map, collect, those sorts of operations, and you'll recognize those if you're familiar with Scala or other functional type paradigms. And then actions, by contrast, are things that like count and fold and reduce, which actually require you to sort of ship data around the cluster. So here's an example of a transformation and an action. In this case, we apply a filter to produce an RDD of persons above the age of 17. Next, we materialize the RDD to obtain a count. So the first part, the filter, is a transformation. The second part, the count, is an action. And here's another example of more detailed, looking at code here, of how we might, how Cassandra and Spark actually integrate using the Spark connector driver. In this example, we load data from the persons table in Cassandra and serialize it into an RDD of type person using the Cassandra table method. And of course, person is a case class, which if you're familiar with Scala, that is essentially, you can imagine if you're using another language, that's just creating a class of person and creating all of the requisite fields inside it. Next, we filter all persons over the age of 17, and then finally save the RDD directly back to Cassandra using the save to Cassandra method. So we actually, in this case, never materialize anything until we write it to Cassandra. So there's no actions here. For those new to Spark and Cassandra, this is quite powerful and skips a lot of the steps previously required through the older drivers. And here is an example similar to the one we just showed, except that we use Spark SQL to filter the persons RDD. And like before, we load the data from Cassandra into a Spark RDD first, and then we immediately use the register as table method to create a table named persons. This will allow us to issue SQL queries against the person RDD. We filter out all persons above 17 using SQL and then print the results. And so it's worth mentioning that this is not Cassandra specific. This actually works against any RDD. And so while this isn't directly related to the Cassandra integration, let's look at Spark streaming as well, because it's one of its key points of differentiation. With the Spark streaming context, we can now process streams just like we can any other data. Spark slices up the stream and produces RDDs on a defined interval. So, and it's basically time windows. So you give it a time window and then you'll get data for that time window. And because it simply produces an RDD, you can perform the same operations on the stream that you can on any other RDD. So it supports a variety of sources, things like Kafka queues, a Twitter, which Twitter is mostly just for playing around. You know, obviously there are some people who might use that for your real analysis, but it's mostly playing around. Things like Flume, if you're doing log aggregation, you know, you can send your data to Spark instead. In this example here, we want to filter tweets we think may be happy tweets. And so how do we define happy word? How do we define happy tweets? We create a set of happy words, and then we use the Twitter utils library, which is part of the Spark streaming, to obtain the stream of tweets and begin to produce a D-stream of tweet texts. We then define a method that searches the text looking for words in the happy words set, and then we use that method to filter tweets we believe are happy and print them to the console. So pretty straightforward. I mean, from a streaming analysis perspective, if you can imagine doing something like this with even a pretty modern API like Storm, this is substantially more straightforward. So then we get an output that looks something like this. I originally had this talk as a demo, but the 35-minute time window doesn't allow for a demo, and I'm not brave enough to do it in front of this many people. So we've seen some simple examples that show how easy it is to get started with Spark. But let's talk about how you structure a Spark application for real-world task distribution. One of the things you'll find if you try playing with Spark is that things that you would think work don't work because, you know, just like CQL makes abstracts a lot of the things going on underneath the hood. The same thing is true here, whereas when we write MapReduce, we have to sort of manually do it and understand everything that's going on. Spark abstracts that, so there's some need to kind of understand what's happening. For starters, RDD operations are similar to the Scala API, but your choice of operations and the order in which they are applied is really critical to performance. You must organize your processes with task distribution and memory in mind. Spark is very memory hungry. The first thing is to determine if your data is partitioned appropriately. A partition in this context is merely a block of data. If possible, partition your data before Spark even ingests it. If this is not practical or possible, you may choose to repartition the data immediately following the load. You can choose to repartition to increase the number of partitions or coalesce to reduce the number of partitions. The number of partitions should, as a lower bound, be at least 2 times the number of cores that are going to operate on the data. But having said that, you'll want to also ensure that any task you perform takes at least 100 milliseconds to justify the distribution across the cluster. And then the next thing, and this is the same thing as with really any data processing pipeline, you want to filter early and filter often. So do things like apply filters, use the where clause, do distinct, those sorts of things early so that you reduce the amount of data that you're processing. And lastly, make use of pipelining. So if you can avoid materializing data and instead use transformations to pipeline that, then you'll find that Spark will do a better job and be more performant. In jobs which require a shuffle, which if you're familiar with Hadoop, it's the same sort of thing, see if you can employ partial aggregation or reduction before the shuffle step, similar to the way you do a combiner in MapReduce. And this will reduce data movement during the shuffle phase. Finally, be sure to match the operations to the required task. Create the simplest and most efficient algorithm necessary to answer the question. So here's a simple example using a query and subsequent filtering to thin the data set. First, we select only the fields we need to perform the analysis, in this case, age and email address. Next, we use a filter to get the over-the-hill demographic. Let's assume this is not the only demographic we're going to process. Otherwise, you would simply include this filter in the CQL statement. We will then apply subsequent operations on the data to complete the analysis. So here are some common tasks that are costly and require a shuffle. So these are the kinds of things you want to be careful about. Things like sorting, reduce by key, and group by key, because they require shifting data across the cluster. These operations require the data to be compared against other data elements, which is expensive. So it's important to learn the Spark API well to choose the best combination of transformations and where to position them in your job. So that's mostly what I had to talk about today. I also have to make sure I give you a shameless book plug. If you're interested in deploying Cassandra for high availability, which I'm sure we all are, then this is, here's a preview. You can check that out coming out this month. Otherwise, I appreciate your time and look forward to any questions you might have. Do we have any questions? Yes?
So you said that Spark is really memory hungry. So what happens if your jobs are effectively just trying to use too much memory? Does it just start to thrash? Does it, like, what's the failure mode?
So if I understand your question, you're saying if you try to run a job that requires more RAM than you have available, what will happen? So it kind of depends. In most cases, what we have seen is that things will start to fail, and it will report back that it is unable to allocate sufficient resources for the job. So there are some things that it can spill to disk on, but you can't really rely on that for everything. Sorry, the lights are very bright. Right there.
So are you running Spark and Cassandra the same cluster, or there is a shared and separate cluster?
So if you're familiar with doing Hadoop analysis, the sort of canonical way of handling this with Cassandra is you use data center replication. So you have an analysis data center that is usually virtual, so it's co-located with an existing physical data center. So you have essentially a transactional cluster, a transactional data center, and then an analysis data center that's getting replicated data. And the one thing I would say too is be careful about vnodes. I didn't say this in the talk, but be careful about vnodes when you do this. It's a good idea to run essentially a single token on each node, because otherwise it will 256 if you run the default number of vnodes. That's the minimum number of splits you'll get, and that's not always what you want.
Have you guys evaluated resource like framework, which can run, which can be, heterogeneous clusters can run the same framework? Have you guys?
You're talking about heterogeneous, meaning like Spark and Hadoop together?
Yeah.
No, we actually run, we still have some existing MapReduce jobs, and we do that. So it's, you have to manage resources a little bit better. There are some tools, like for example, Cloudera's tool purports to do this, but I have found it not to be very good at doing that. So you really kind of, if you're going to do that, you have to kind of manage it yourself right now. I'm actually very interested if someone is aware of a tool that does that well, because we would love one, and we might end up building one if that doesn't exist. I thought I saw someone else's hand up.
So what is the use case of the weather channel? How do you use for your purposes?
Well, one of them is what I showed you, the histogram. That's obviously a very rudimentary use case. Our primary use case is event analysis. So, and by event, meaning a similar sort of thing to the event talk you might have seen this morning if you went to that. But we have a generic event API that does, we ingest about depending on the day, between 3 and 5 billion events per day. And those events all go into Cassandra. And then, so essentially what we do, we're running on AWS, and we have those events go into an SQS queue. And we wrote an SQS Spark streaming connector. And so they go into a queue, they get pulled out on the other end, and then sent, some of them get sent to Spark streaming, but all of them go directly into Cassandra. And so that's essentially our primary use case. And then we do various sorts of analysis on those events. They could be, you know, a user scrolled this far in our app, in one of our apps, and clicked on this content, or, you know, someone reported their requested weather at this location. You know, all sorts of things. Everything you can imagine we capture. Anything else? All right. Oh, there we go. Yes, we are. We're brave. But we're not the first.
Is it really still true that it only works in memory? Because as far as I know, they're changing shuffle algorithm.
So that may be true. I will readily confess to being compared to. I've been using Cassandra since 0.5, so I'm a unicorn in that space. But I'm a relative newbie in Spark, so I will readily admit that. And I will tell you that our experience has been that although they say that spilling to disk sort of works well, that in our experience it doesn't work very well. So we're looking forward to that working better.
Yeah, I think it's improved a lot in the last.
And maybe so. We're still running 1.0. something early on. Any other questions?
This kind of speed up you were mentioning is also for the group by operation, or is just for figure? Because I can imagine that in memory, figure is way faster, but
Yes.
on group by in a distributed environment.
Yeah, group by is always going to require a data shuffle, and so, you know, I mean, there's so many variables in how fast you can distribute a shuffle across the network there's going to be a lot is going to be dependent on, you know, variables outside of Spark itself, and that's why, you know, I recommend that you do those sorts of things sparingly and as after you have filtered as much as you possibly can. Make sense? Anything else?
Can you recommend any good getting started resources for Spark and/or Scala?
Spark and/or Scala. Well, I will say this. In terms, I'll answer the Scala one first. In terms of Scala, there is the programming in Scala book is actually really, really good. That's how I learned Scala 4 years ago. So I highly recommend that. You don't really need to be a heavy Scala developer to get started in Spark, right, with Scala. In fact, Spark is a really good way, I would say, to kind of get into the game, because there's a lot of really esoteric kind of features in Scala. And the only bit of advice I would give you in learning Scala is don't get too worried about what the zealots say on Stack Overflow, because it can be, you know, you can get some really intense and, you know, crazy conversations going on, and just, yeah, I do recommend trying to write Scala in a functional way, but at the end of the day, it is a functional OO language, so, you know, you can wade in little bits at a time if you want to. As far as learning Spark, actually the best resource that I've found so far is the Spark website. You know, it's a lot of experimentation. In many ways, it's where Hadoop was years ago, where we were all sort of trying to figure out what the design patterns are. So that's what I would say. Anything else? We're done? Okay. All right. Thank you very much.